Welcome to another Coding Like Mad Python tutorial. In today's tutorial, I'm going to show you how to use the keras and Tensorflow frameworks to build your first neural net. This is intended to be a beginner tutorial, so we're going to focus on things like setting up your environment, as well as what individual lines of code are doing when you're building your neural network. If you're interested in just the quick start guide, I'm making one of those as well, and you can get it in the link below if you're interested in that. So to get started, I first need to introduce a little bit about how this tutorial is going to go. In biological systems, neural networks compose the nervous system of the organisms. These neural networks are responsible for all calculations that an organism does, which are more complex than simple chemical reactions. For instance, in humans, neural networks are responsible for things like processing vision, as well as synthesizing speech, logic, and pretty much everything else our brains do. This has inspired computer scientists to develop artificial neural networks. Artificial neural networks and biological neural networks do share some similarities. In particular, both accept a number of inputs, apply a nonlinear function, and then send out a number of outputs at each neuron. However, that's as far as the similarities go. In practice, a biological neural network is more like a spike network. This is a type of network which takes advantage of time differences. It's sort of the difference between AC and DC electronics. But that's as far as we're going to go into the theory. What's most important for somebody using a neural network to know is that they can calculate just about anything. They're universal approximators. For any input signal, they can generate an output signal. For the rest of this tutorial, we're just going to focus on how you use them. So to get started, I first need to introduce a little bit about how this tutorial is going to go. I'm going to be working with something called Google Collaboratory. This is a free environment that basically anyone can use and gives you access to GPUs. Everything I'm doing in this tutorial, though, can work in pretty much any other environment. If you want to be working in PyCharm, for example, that's totally fine. Everything I'm saying is going to work. In the code, in the descriptions, you'll see a couple notes that say particular lines are required specifically for Collaboratory use or Google Colab use, but if you're working in those environments, you can just take those lines out. It's not a big deal. So to get started, I'm going to show you how to get the Google Colab environment set up. Google Colab has the necessary libraries already installed, so we don't have to add anything. In order to avoid compatibility issues, I think it's pretty important that people are using Tensorflow 2.x as well as the version of keras built into it. Oftentimes I find tutorials don't work properly or even have bugs in them, which are avoidable if you're using the most recent versions of the software. So the first thing to do is we're going to want to have a GPU runtime established. Basically, we want a virtual machine that our Google Colab session can connect to that has an actual GPU in it. We can do this by going to the Runtime menu and going to change runtime type. Here you'll notice I've selected GPU as my hardware accelerator. This makes sure that I actually have a GPU available so that I'm able to access that functionality. Tensorflow is going to automatically detect it's there and work with it. You actually need to kind of force Tensorflow not to do this, assuming that you have all the libraries correctly installed. So, having set up our runtime correctly, let's go ahead and verify that I have access to a GPU. The code that I'm going to show below is code which allows me to not only check what type of GPU I have gotten access to in this session, but it's also going to let me mount a copy of my Google Drive. In this case, I've created a folder called PyMLTut inside of my Google Drive. This is going to be a workspace where I'm going to be able to save some data and so forth. Again, all of this is going to work just fine if you're working in PyCharm. You just have to go to a specific directory. So let's go ahead and run this code. We can do that by going to the runtime environment and clicking Run All. At this point, it's going to pause the session, as you can see here, and request permission to access my Google Drive. To avoid releasing a whole bunch of confidential information, I'm going to go ahead and cut this part from the video. Once you've clicked allow, you should be able to see what was actually included. So not only are we going to see that we have successfully mounted the Google Drive, but we also actually get to see what particular GPU is available on this runtime session. Because I'm working in Pro Plus, I actually have received access to a V100 in this particular session. There's no guarantee that I'm going to get a GPU this good every time. It depends on the availability. My experience has been that generally at the free tier, I'm getting access to K80s. At the lower Colab tier, I was getting access to P100s, and at the upper tier, I'm getting access to V100s. It's worth noting that a V100 is a machine worth far more than any other piece of hardware I own. So having access to 2 of these sessions is actually, in my view, an amazing deal. Anyway, not sponsored or anything for Google Colab. I just have become very much somebody who's a fan of their service. One of my complaints about machine learning tutorials is that the vast majority of the ones I see fall into kind of one of 2 categories. Either they fall into the 6 lines of code and you're going to be able to make millions on the stock market category, which is absurd, or they fall into the category of diving deeply into the mathematics and not really explaining how to practically solve a machine learning problem. In today's tutorial, I'm going to try and balance those 2 things by showing you how to solve a regression problem. This is a problem where we take some inputs and we generate out a continuous number in a response where we know what that number should have been. This is as opposed to a classification problem where we're trying to say that, for instance, a photograph might contain a cat or a dog. You'll notice it's one or the other as opposed to 0.3 cat or 0.5 cat. For instance, we might like to predict what is the temperature tomorrow, or we might like to predict what is the value of a stock going to be tomorrow, or even what is the probability that a particular person has cancer based off of the values that we've given them from their test results and images. This is a very simple problem, but that's kind of why I wanted to focus on it, because it's an incredibly common problem, it's a very powerful problem, and pretty much every problem you're going to run into when dealing with more advanced problem types is going to show up here first. So by understanding this type of problem, we're going to be able to deal with those more advanced problems more easily in future tutorials. As well, if you don't know how to do this properly, you absolutely aren't going to know how to deal with any of the others properly. The good news is you've probably actually seen this type of problem before. Most people in a science class have actually had to do something called curve fitting. So we're actually going to be comparing the results of our neural network to a polynomial each time. The curve I've chosen is actually a very complex one. It looks like this. So you'll notice that this isn't a function which you could easily guess. And that's part of the strength of neural networks. They're able to handle an arbitrary function type, whether that function be continuous or discontinuous, whether that function even has a single value or is probabilistic in nature, whether that function is fully describable with the information on hand. In all cases, it's going to be able to find a best estimate of what the function's behavior is. As long as there is a well-posed problem, it will be able to find a solution for it. That doesn't necessarily mean it's going to be the right solution, but it will be the best solution given the data that it has. Now that we have our function, we can go ahead and generate some data with it. In this case, we're going to use some NumPy functions which are going to generate numbers on a pre-chosen range. It's important to note that this is one of the first pitfalls that you might run into with any kind of machine learning problem. We have chosen a range in advance here. We're going from -15 to +15. In the event that we attempt to evaluate our function outside of those values, we are likely to have an issue because our model isn't trained outside of those ranges. There's a validity range of our model which is being imposed by the initial training data. If we have more training data, we might have a wider range. This limitation is important to keep in mind. Here, being outside of the range -15 to +15 can cause problems. In the stock market, the fact that you've observed something in the past means everyone else has observed it too. You were dealing with a training situation where everyone else was naive when you trained your data, except all of the other people on the stock market are not naive, and this is how you can lose an awful lot of money very quickly. So Now that we have generated some random uniform values, we can go ahead and also generate the curve itself. So I'm going to generate 1,000 data points and basically make a plot of all of this. So let's take a look at what our actual plot looks like. And you can see that the true values are overlaid with some observed values. We have these 15 data points to deal with, but the actual curve has behavior not caught in those data points. For instance, you might think that it should stay low after the first data point if you go any further below, say, -12, but it can actually go up after that point. Similarly, you might think that it is just trending upwards in the last half, when in fact it's not. It's actually oscillating quite rapidly. So these are all different features which are difficult to capture with the information that you have. You need to interpolate in as smart a way as possible. Of course, in real life, data doesn't actually just fall along the points. Every measurement that you have has a certain uncertainty to it. In order to model this uncertainty, we're going to add some Gaussian noise to our data. This is quite easy to do. In the case of real life, of course, you don't necessarily want to add noise to your data, but for our contrived example, we definitely want it there. Again, if we run this, we're going to see that now we have generated some additional noise, which makes it even more difficult to see what's going on. So let's go ahead and actually make a neural network. In this case, we're going to be using the keras front end for TensorFlow. As I mentioned, this is actually built into TensorFlow at this point. And we're going to be using something called a sequential model. Sequential models are essentially models where each layer has precisely an input and an output. This is as opposed to a functional model API, which Keras also has available, where multiple inputs can result in multiple outputs in order to create what you might think of as a branched network. So now that we've created our model, we need to start specifying the different layers within it. And you do this sequentially with a sequential model. Not surprising, really. So the first thing we do is specify an input for the model. This is an input which provides the shape of the incoming data. Here, because our function was simple, there was a single x resulting in a single y, we just have a dimension of 1. If we had a multivariate input, we would specify, for instance, for a 10-dimensional input, we would specify 10 parameters here. For this extremely simple neural network, we're going to be using a single dense layer sandwiched between the input and the output. We have 1,000 neurons, which are going through an ELU activation function. Now, activation functions are the main things that make a neural network different than just a pile of linear algebra. In this case, you might typically see a ReLU function, or a rectified linear unit. The rectified linear unit, or ReLU function, is 0 when it's negative and is a linear function when it's positive. However, the ELU function improves this a little bit by smoothing out its behavior and allowing it to go to a negative value close to 0, but not quite 0, and avoid that discontinuity in the at the 0 point that you see in the ReLU function. These 1,000 neurons are then connected to a single output. We need to have a single output here because we're actually predicting a value that has a single dimension. And that's really it. We can go ahead and actually display a summary of the results, and if we do that, you'll see a text summary of what is actually in our model. In particular, this is a good practice to get into so that you can understand exactly how complex a network you made and did you make the thing you intended to. So as you can see here, we have 2 layers in the neural network which have parameters in them. In the first layer, where we have a single output going to 1,000 neurons, we actually have 2,000 parameters. Now, you might be a little bit surprised by that, but the reason is that each of the inputs is running through a simple equation. We have a slope times the input value plus an offset being fed into the activation function. This means that there are 2 parameters for every neuron. Similarly, we have 1,000 values in the output. Each neuron is providing a single number to the final layer of the neural network. Here, all of that is getting compressed down to a single value. This time, though, we essentially have one slope value annotated by that W in our math on screen, plus a constant that is being run through our linear combination. Now, the linear activation here just means go ahead and activate this as though it was a constant value. So the result of this is we're basically just adding together everything in the previous layer with an offset. Normally in a network like this, I like to have an activation function which is linear in the last layer, purely so that I can combine different parts of the previous layers in kind of an intelligent way. It lets different neurons focus on different things, and then I combine them as a weighted sum at the end. Finally, you'll notice that with 3001 parameters, this is actually a lot more parameters than a typical polynomial for this would have. This seems a little bit strange at first, that this could ever possibly work with a small amount of data, but what is interesting is in practice, many of these neurons and many of these parameters are not really going to be that important to solving the problem. It's more like we've given it lots of opportunities to figure out how to solve the problem, and it will discard the parts of it that aren't turning out to be helpful. We're going to come to some techniques later on for avoiding the overtraining problems that you would normally see with a problem like this, and you'll notice there that the number of parameters often vastly exceeds the number of training points. Next up, we need to actually compile our model. This is essentially telling TensorFlow to take the sequential model that we've made a graph for and turn it into something that it can actually work with. You'll notice that I've specified an optimizer, a learning rate, and a loss function here. In turn, these are the three most crucial things that you're going to be specifying for every model you ever make. The optimizer's job is to take the data and the current model and optimize it, set the parameters in it. So those 3000 parameters need to be set according to a very complex piece of mathematical code, which is going to try and find the best fit for them. In this case, that's all being done by the atom optimizer. The atom optimizer is probably the most popular optimizer that is in use today, although you'll often see arguments over whether SGD with carefully chosen parameters is actually going to outperform it. The learning rate here is one of the key parameters of your neural network. Essentially, the learning rate tells the optimizer exactly how much it should change things on any particular update. A higher learning rate will result in a faster convergence. However, by having a higher value, you're more likely to memorize data and overtrain. You're also more likely to miss out on local minima, which could be really crucial for solving your problem. So I won't get into the detailed ins and outs of this, just be aware that it isn't so clear-cut as to say that higher or lower is better here. Often a mid-range value, for example 0.001 or 1e-4, will result in the fastest convergence, despite not actually resulting in any individual step being fastest. Another way to think about this is you're asking the optimizer to be careful, but not so careful that it's taking forever to get there. The final parameter, the loss function, is being set to MSE. This stands for mean squared error. As you can see from the equation on screen, this basically is going to be telling the optimizer to minimize this equation in order to make our function match the data as closely as possible. There's a lot of reasons to appreciate MSE, not least of which it has some close ties to the probability of the noise distribution. The noise distribution we chose, Gaussian, actually results in a mean squared error distribution precisely fitting the data. This assumption helps us actually fit the data correctly. Conveniently, it's also the assumption which is being used by polynomial fits behind the scenes. So this is a very common, and in this case, apples to apples comparison. Finally, we're going to need to go ahead and actually train our neural net. As you can see here, we're going to be adding an extension called TensorBoard. TensorBoard is a way of visualizing what happened during our training. It's an incredibly powerful tool. And again, while here I'm showing how to load it on Google Colab, you can of course still use this on PyCharm. We're going to create a callback when we do this. Essentially, callbacks are functions which the neural network training code is going to occasionally call. In this case, it's going to record statistics about how things were actually going during training so that we can go back and look at the actual performance of that training later. And then last, we just call model.fit with the X and Y data specified. We've also specified the batch size and the number of epochs. Batch size is simply the number of data points which are going to be looked at by the optimizer at once. You might think that the best thing to do would be to give all of the data points simultaneously, but that's not always the best decision for two reasons. First of all, when you are dealing with more complex data, for instance, if you are dealing with frames from a video, the amount of data stored in a single batch is absolutely massive. As a result, you can't look at the entire movie at the same time. As a result, you need to look at parts of it at a time and train accordingly. The second and maybe less intuitive part of this is that having a smaller batch size allows the data to be explored more dynamically by the optimizer. In other words, every time it tries to fit a subset of the data, it might come up with a better local minimum. In other words, it seems that having a higher batch size results in effectively a lower learning rate. In practice, the batch size and the learning rate have a bit of a trade-off with each other, but it isn't quite one-to-one. So as a result, you're going to want to tune the batch size in the same ways that you tune the learning rate in order to get the optimal convergence behavior. The epochs is simply the number of times that the data needs to be looked through in its entirety. In this case, I'm instructing the fitting system to look at all data 1,000 times in batches of 16 pieces of data at a time. So to run this, we just click the start button and can see it now progressing through our epochs. You'll notice that this is going quite quickly. This isn't surprising because putting this on a GPU worker is actually a pretty big misuse of the GPU. 28 milliseconds per step is relatively fast, but almost all of that time is probably being spent in wasteful operations because I'm only looking at a very small number of data points. And you can see that in just a couple of minutes, we have successfully moved our way to all 1,000 epochs. You'll also note that I'm always getting the loss values from each iteration. This is essentially the thing it's trying to optimize. So if I scroll up, you'll notice initially it was 56,000, 57,000, scroll way up 68, 70, started at 142,000, and by the end I'm down at 53,000. So you can actually see the improvement in performance. Ideally, the number of epochs should be high enough that it is able to minimize this down to the lowest possible value. Of course, this is going to result in a certain amount of overfitting, and we'll talk about techniques for avoiding that a little bit later on. Another critical step is you're going to want to actually save the outputs of your model. So in order to do this, we're going to use a model.saveWeights command. This is just going to save the weights. You need to remember what the network is itself. And I recommend that if you're going to be training many models, that you actually serialize it properly. I'm not going to go into that in this video, but you can find instructions very easily on the TensorFlow website for it. Next up, we're going to take a look at the actual TensorBoard output. The TensorBoard output is the results that were stored in the log directory that we selected and tell us basically how our training actually progressed. What you'd like to see here is that it's basically converged towards the end. If you're not running in Google Colab, this is actually going to be done in your browser anyway. When you run TensorBoard, it will open up a port and you'll just be able to go to an IP address it specifies and look at the output there. You'll notice that there are two lines being showed here. They've been labeled with different dates. One of them is today, which is December 20th. The other was December 13th when I previously was working on this tutorial. You can go ahead and hide those earlier ones and just look at the one that you're interested in. If you want to get rid of these, you can of course delete the directory or potentially just use a different subdirectory lots of options. In this case, because we are only recording the loss, we were only monitoring a single value, but TensorBoard's nice in that I can see many different things about this data. Potentially things like the graph for the model are available, for instance. In this case, you can see that it is a sequential value, that I'm using the atom optimizer, and that there are various operations occurring in the background. I'm not going to go into great depth about this, but there is quite a bit of information available via TensorBoard here. You're also able to see some of the histograms of performance and other detailed information that helps you make the most sense of what is going on. So let's go ahead and see how well things actually did. We know from TensorBoard that our fit seemed to be functioning correctly, but we haven't actually looked at the output from it. I can do that by predicting the values of the function using our model and the .predict method. I'm basically just going to plug in those 1,000 points we had originally and then put them over top of the original function. And what you'll notice is that it's a very simple fit. This is the advantage of using a method like a neural network, which is able to create constant fits in the absence of other information. Now, you might think this isn't a great fit, but on the other hand, what function are we actually looking at here, right? This is incredibly noisy. It's come to the conclusion that there is a increasing function and then a decreasing function and then a slight increase to it. I don't know that this is particularly a bad fit. I also don't know that a particular polynomial would necessarily have done better. It just is what the output is. And we're going to talk about techniques for how to evaluate the performance of a model a little bit later on in this tutorial, because that is really the crux of it. When should you use a neural network? When are you getting the best results possible? And how do you evaluate that? How do you evaluate that you shouldn't have been using a different model, a simpler model like a polynomial fit? We'll talk about that, and I think it's one of the key steps in being able to practically use machine learning techniques. Now that you know how to build a basic neural network in Python, pretty much everyone has the same question. How many layers should I be using? How many neurons? And what activation function? The answers to this come from a process called hyperparameter tuning. We're going to talk about that in part 2 of this video, linked below. This video series is planning to cover a bunch of advanced topics like convolutional neural networks, recurrent neural networks, and reinforcement learning. If there's a specific topic that you are interested in, be sure to mention it in the comments below and we'll see what we can do. I also answer questions about the content there too, so feel free to ask. I hope you enjoyed this video, and I'll see you next time.